This is an optical compass I made, and it always points to where the sun is in the sky, no matter how I turn. That's because the sunlight leaves a hidden directional pattern across the sky that's completely invisible to us, but not to bees. Bees have been using this exact information for millions of years, encoding it into something called a waggle dance to tell other bees where to fly to find food. In this video, I'm going to show you why the sky becomes polarized even when the sunlight that illuminates it is not, and how bees use this information to create a map of the sky and give precise directions to one another, and even how modern companies are now using this same optical pattern to navigate when GPS signals are jammed. Now remember that light is a fluctuation of electric and magnetic fields. For example, if I take an electric charge and wiggle it in space, I'll get an electric and magnetic field that looks like this. The electric and magnetic fields are perpendicular to each other. But let's just look at the electric field. With one wiggling charge, if you look straight down the barrel of this field, it looks like a line. So we say that this is linearly polarized light. But the light coming off the sun is not polarized. What that means is that for any given ray of light, it can have any linear polarization. So the line could look like this, or like this, or like this. So the light from the sun is this mixture of all the linear polarizations of light. But something interesting happens if the light bounces off the air first. Air is made up of molecules with charged electrons around them. When the electromagnetic waves from the sun hit these electrons, they cause the electrons to oscillate as well. Now that the air electrons are oscillating, they become oscillating charges themselves, and oscillating charges radiate electromagnetic waves. But what do these new waves look like? Well, we can model it by looking at the oscillating waves of a dipole antenna. You can see that the waves that are emitted aren't equal in all directions. If you're right above or below the oscillating charges, then you don't see any waves. But if you're in front or behind any direction, you'll be hit by the waves. So any waves emitted from a dipole antenna or anything like a dipole antenna are linearly polarized. In 3D, the waves emitted from the dipole look like this donut shape here. So when the electrons are oscillating up and down from you, it's like you're inside the donut. You can't see any light. So this means that when light from the sun that is polarized oscillating up and down hits the air, then the emitted waves from the air radiate out with the node below it. But when the light from the sun that's polarized oscillating like this going in and out of the screen, then the emitted waves of the air are now rotated 90 degrees as well, and a person below it is now right in the path. So the sky acts like a polarizer, not by blocking light, but by preferentially sending one polarization of light down to us. So that's why we see light coming from the sky even when we look away from the sun. If there were no air and you looked up at the sky, you would just see the stars even during the day. This whole process is called Rayleigh scattering. And by the way, the higher the frequency of light, the better this happens. So this happens for blue light better than red light. So that's why the sky is blue and why it's polarized. And I can check whether light is polarized using a polarizing filter. This only lets light through proportional to its polarization direction. When it's aligned with the polarized light, it lets it all through. But if it's rotated a bit, it lets only some of it through. And when it's perpendicular to it, it blocks the light completely. Now, if we look at the light coming off a computer screen, we can see this easily. Screens emit linearly polarized light, so rotating the polarizer makes the screen brighter or dimmer. And sure enough, if I take this outside and look up at the blue sky, I see the same effect. The sky gets darker or lighter depending on how I rotate the polarizer. So the blue sky is indeed polarized light. But how do bees use this? Well, the polarization of the blue sky isn't uniform. It depends on your viewing angle relative to where the sun is. The most polarized light is always at a 90-degree angle from the sun. And if you map out the whole sky, you'll find that the polarization directions form concentric circles around the sun. With a single polarizer, you can't see these lines though. You just see dark or light. But bees have evolved a specialized region of their eye called the dorsal rim area, which is dedicated entirely to sensing polarized light from the sky. So I'm going to try to mimic this organ by cutting up a bunch of polarizing sheets. So if I take a polarizing filter and divide it into narrow strips and then form wedges, I can arrange these strips in a circle at different angles. This device is called an optical compass. My son even designed a nice frame to go around it using our new printer. So before I show you how bees use this type of mechanism to find food, I want to thank Creality for sponsoring this video and sending me their new Spark X i7. This printer is incredible. You can literally take a photo, turn it into a 3D model, or take an idea and turn it into a multicolor print with basically one tap. The AI handles all the hard parts, so you can focus on creativity instead of settings. The setup for this printer was incredibly smooth. From unboxing to first print only took about 5 minutes. It auto-calibrates, guides you through setup, and just starts printing. No leveling, no tweaking, it just works right away. And once it's running, it's basically hands-free. There's one-click model selection, automatic calibration, and real-time AI monitoring that catches failures before they turn into spaghetti. And the RGB status lights also let you know what's happening at a glance. And what's really great about this printer is the multicolor printing. With the CFS unit, you can print in 4 colors with automatic filament switching and clean transitions, opening up a ton of creative possibilities. The surface finish is incredibly smooth, and the micro details are crisp thanks to a vibration compensation and precise flow control. So whether you're a beginner, a student, or just want great printing, the Spark X i7 is a fantastic option for you. If you want to check it out, I'll put a link in the description. Now let's get back to our experiment. Now when I take this optical compass outside and look at the sky, you can see a dark line running through the circle. And the amazing thing is that as I move it around, the dark line always points along the direction of the sun. So no matter where I look in the sky, I always can tell where the sun is. So now watch, if I follow this dark line, it'll lead me straight to the sun. But you can get even more detail than that. Near the horizon, the dark part isn't as dark, but closer to the sun's path in the sky, it has much more contrast. So notice how it's not so bright here, but then I move more up to the straight up position. Now you can clearly see the dark lines. And as I move around the sky, those dark points always stay pointing towards the sun. The sun's over there, really bright. Ugh. And if I map this out, I'd get a full polarization map of the sky. What's amazing is that I don't have to see the sun at all. If I can see any patch of sky, I know the sun is located somewhere along this line. The sun's not even fully risen yet, but still, it points to it. So bees' eyes can see this polarization line just like this optical compass. So all they have to do is look at the sky and they automatically know the direction and angle of the sun. They don't even need a direct view of it. They can be under a tree, or the sun can be hidden behind clouds, or not even risen over the mountains yet. So if they find a nice little field of flowers, for example, they know exactly where it is relative to their polarized sky map. But what if they want to tell another bee about this field? Well, they need to communicate that position on the sky map. So all they need to do is be able to communicate the angle relative to these polarization lines pointing at the sun and the distance to fly at that angle. So inside the hive, all the bees feel gravity, so they know which direction is up and which direction is down. So if a bee wants to say fly straight towards the sun, it waggles straight up the hive. If the food is 30 degrees away from that polarization line, it waggles 30 degrees away from vertical. If the food is directly away from the sun, it waggles downward. And the distance they should fly is encoded on how long the waggle lasts. It depends on the species of bee, but a waggle of about 1 second means about 1 kilometer away. So a 45-degree waggle for about 0.6 seconds means fly at 45-degree angles from the sun polarization line for about 600 meters. The bee repeats this waggle dance over and over, and the more excited the dance, the better the food source. And if other bees verify it and perform the same dance, the signal gets amplified until the whole hive knows where to go. Scientists have actually tested the bees' dependence on polarized light. In a classical experiment, biologist Carl von Frisch, who later won the Nobel Prize for this work, rotated an artificial polarization pattern visible to bees, and the bees rotated their waggle dance the exact same amount, proving that they were following the polarization of the sky and not the sun itself. Now, the ability for bees to read polarized light from the sky and encode it into a dance that communicates direction and distance has to be one of the coolest things found in nature. It's so ingenious that this same idea has inspired modern technology. For example, there's a company that develops optical polarization sensors that help drones and autonomous systems determine direction using the sky alone, essentially giving machines a version of a bee's optical compass. And thanks for watching another episode of the Action Lab. I hope you enjoyed it. If you have any questions, let me know in the comments section, and I'll see you next time.